Hi, everybody. Welcome to AP Physics C Mechanics. My name is Angela Jensvold, and today we're going to review angular momentum. Take a look at this question. Okay, so here's the deal. If you guys remember Newton's second law, hope you can see that. You guys remember this? Says that the sum of forces equal to the rate of change of linear momentum. Well, the rotational analog for that is the sum of the torques is rate of change of angular momentum. Well, this figure skater is on ice, so there is negligible friction, so no external torques acting on the skater. So that means that angular momentum is conserved. In other words, the rate of change of angular momentum is 0. Okay, so that means that her initial angular momentum, which is, by the way, rotational inertia multiplied by angular speed, should be the same before and after. And then it's asking about kinetic energy, right? So rotational kinetic energy is 1/2 I omega squared, right? That's rotational kinetic energy. So what happens here is when she draws her arms in, the rotational inertia decreases, right? So if I final is smaller, is decreasing, then omega final must increase by the same factor. And if you come back over here to rotational kinetic energy, the rotational kinetic energy depends on the square of the angular speed. So the fact that the angular speed is increasing is a bigger factor. So kinetic energy of the skater should increase. Okay, we're going to look at 4 learning objectives, and these are the main ideas. Sorry, guys, there's something wrong with my screen. I never know how to get out of this. Okay, I can only see half my screen. Okay, so angular momentum is a vector, and it's equal to rotational inertia times angular speed. And then, well, this is the rotational analog of linear momentum, isn't it? Right? And then this kind of looks familiar. This is angular impulse. That reminds me of the integral of force with respect to time is equal to the change of linear momentum, right? So that's angular impulse. And then we talked about this one, the sum of the torques, that's just Newton's second law, is equal to the rate of change of angular momentum. Okay, I cannot see the other one. I know it's the definition of angular momentum, R cross P, but oh gosh. Okay, thank you. Thank you for your patience. All right, now this one is if you have an object that's moving, that's not spinning, but moving in a straight line, then you can use the position vector cross the momentum vector. The vector R starts from the origin of your system, and it goes to the position of the particle. Okay, so we talked about this. If there's no external torque, angular momentum stays constant, and then angular impulse is equivalent to the change in angular momentum. Okay, first item on our agenda today is to go back to what I said Tuesday. I made a remark that I regret. And I want to go, so I was solving part A, which is the acceleration of the center of mass. So here's what I did. I said, obviously, I start with a force diagram because I'm no fool. Force of the Earth on the hoop. Well, actually, I was a fool later on, but anyway. Normal of the ramp on the hoop. And then we have friction of the ramp on the hoop. Those are the three forces that are acting. And I broke the Earth's force into components. So this component here would be mg sine theta. So I did acceleration equals sum of forces over mass. And the force down the incline is mg sine theta. And the force up the incline is friction. And then I substituted in mu normal and I backtracked and I didn't end up going that way, but I made a comment saying, oh, that wasn't wrong. We could have done it that way. Well, no, it was wrong. It was totally wrong. And let me explain why. You know that kinetic friction is equal to mu normal, right? It's equal to mu normal. This isn't kinetic friction, is it? This hoop is not sliding down the ramp. This is static friction. And I hope you know that static friction is less than or equal to mu normal. It's only equal to mu normal when you've reached the maximum force of static friction right before it starts to slip. So there would have to be something in the problem that said, you know, let's say you had something on a plane and then it says it's just about to slip. If it's just about to slip, that means force static friction is the maximum, right? We don't have any clues like that. So I shouldn't have done mu normal ever. And once I realized I made the mistake, I shouldn't have said that, oh, it would have been fine to do it that way. Okay, so I just want to point that out. And I want to thank Mr. McManus for setting me straight on that. I really appreciate it. Okay. Okay, try this problem, please. Okay, so it says drive an expression for angular momentum. Well, angular momentum is I omega, right? So what that means is we need to find the angular speed of the cylinder at some random vertical distance h down the incline. So I think what we can say, if we say the cylinder Earth is our system, then energy will be conserved. So the cylinder Earth system starts off with gravitational potential energy, and it ends up with translational kinetic energy and rotational kinetic energy. Okay, so did they give us? Okay, so we need to V is omega r, right? So let's plug in omega r here. And they gave us the rotational inertia is 1/2 mr squared. And then we can cancel all those m's, can't we? That's nice. Okay. And then you'll get GH equals 1/2 plus 1/4 omega squared r squared. I don't know why that was so hard for me. So that's 3/4. So 4/3 GH over r squared is equal to omega squared. So omega is 2 over r square root of GH over 3, right? Did I do that right? I think so. Let me make sure. 2 over r. Yeah, I think that's right. Okay, and then it says, is the angular momentum of the cylinder conserved? Okay, well, what did we say about the law of conservation of angular momentum? We said the sum of the torques is equal to dl dt. Okay, is the torque about the center of mass in the cylinder 0? No, there's a frictional torque. If there wasn't a frictional torque, it would slide down that incline. It wouldn't roll. So no, it is not. Okay, we're continuing the same problem. Okay, so you want to find the rotational inertia of the whole yo-yo. So let's start with the inner cylinder. We know cylinder is mr squared, and they said this inner cylinder has a mass m, radius r. Okay, and then both outer spheres. So let's double whatever each outer sphere is. The outer sphere is still a cylinder. They still have mass m, but their radii are 2r squared. Okay, now we got to do some math. 4 times a half is 2 times 2 is 4. What is that, 5 halves? No, 9 halves, mr squared. It's hard to do math in your head. It's a little dangerous. I hope you guys got 9 halves. Same problem. Continue. Okay, so first we'll do our force diagram. So we've got normal of the ramp on the hoop. Is this a yo-yo? Then we have the force of the earth on the yo-yo. And then we have friction of the ramp on the yo-yo. Let's see if we can stay out of trouble today, because they're going to ask us the linear acceleration of the toy. Okay, so I hope you guys were able to get that during the 2 minutes, because we basically just did it a minute ago, but let's just do it again. So acceleration, sum of forces over mass. Now what I'm going to do is I'm going to break this. Oh man, I shouldn't have written there. I should have labeled it on the other side. I'm going to put my force of the earth on the yo-yo over here. Okay, so break it up. This component here would be mg sine theta. So down the incline, you have mg sine theta minus friction up the incline. Okay. So, but we don't know what friction is. So that's why we need to sum the torques. We need to analyze the torques. So let's apply Newton's second law for rotation. And well, alpha is A over R, right? And then the torques, well, the only torque acting on this thing through the center of mass is the frictional torque. So it'd be friction times radius over, now we already got the rotational inertia. Wasn't it 9/2? I think we already got I. Where did I put it? Didn't we get I? Oh, 9/2 mr squared. Okay, so it's 9/2 mr squared. All right, now take that expression. I'm going to cancel all these r's. They all go away. And then I'll get friction is 9/2 ma. So if I plug that into my Newton's second law for translation, I will get ma equals mg sine theta minus friction, which is 9/2 ma. And now I can solve for a. Oh, I made a mistake. I'm going to give you 10 seconds to find my mistake in what I just wrote. Okay, I'm estimating that was 10 seconds. Did you guys find my mistake? Actually, I had a mistake all the way up at the top, now that I'm realizing it. What is the mass of this yo-yo? Is it m? No, it's 3m. Each disc is 3. Each disc is m, and there's 3 of them. So I should have had 3 and 3. It's okay. We didn't get too deep, and we can still save it. All right, let's cancel those m's, especially because look how sloppy I was. I made this a lowercase m. Let's just get rid of it. All right, so 3 plus 9/2, that'd be 6 of 15/2. Oh, I already got rid of those m's. Why am I? A equals 3g sine theta. And we're looking for A. So divide by 15/2. So it'd be 2/5 g sine theta. Is that right? Yeah, okay. All right, then determine the force of friction exerted on the toy as it rolls down the track. Well, we know friction is 9/2 ma. So come back. Oh, how did I don't even know how to do these arrows. Okay, I'm going to erase these. The other ones look kind of cool, so I'm just going to leave them and pretend it was intentional. 9/2 m times a 2/5 g sine theta. So you get 9/5 mg sine theta. Is that what you guys got? Just make sure. No, I made a mistake somewhere. Do you guys see the mistake? 9/2 g 2/5 9/5 friction. Let me see. Oh no, that's right. Okay, time to move on. Oh, it's a long problem. Okay, hopefully this is the last part. Not that we're not having fun. Go ahead. Okay, so we want to find the kinetic energy. Well, kinetic energy, it has translational kinetic energy. It also has rotational kinetic energy. So again, what is the mass of this yo-yo? It's 3m because it's made up, it's composed of 3 cylinders. And I is, what did we find out? 9/2 mr squared. And omega is v over r, right? So this is v squared over r squared. Let's cancel those r's. Get rid of the r's. Cancel. Why am I canceling these m's? You can't do that. That is illegal. Okay. Then 1/2, this is 3/2 plus 9/4 mv squared. So what is that? 6 plus not 15/4 mv squared. Is that what you guys got? Hope so. Okay, try this one. Okay, so first we need to find the tension in the cord. So this whole thing is an equilibrium. So if we just look at this as our system, you would have tension of the string on the blocks, and you would have the force of the earth on the blocks. And when it's in equilibrium, the acceleration is 0. So you would have tension, the string on the blocks should equal, there's a mass of 2m, so 2mg, right? So then it says one block is removed. So I guess what we'll do is we'll put another block here of mass m, and then we'll get rid of that block. And they want us to find the tension. They're calling this tension 3, and they're calling this tension 1. Okay. So let's draw a force diagram. We've got 3m, and it's accelerating. The 3 blocks are accelerating downward at an acceleration of g over 3. So you know that the force of the earth on the blocks should be bigger than the tension of the string on the blocks. Okay, so for this, you would do acceleration is sum of forces over mass, and you know it's g over 3. So that would be 3mg minus t3 over 3m. Okay, so I guess I can cancel these 3's. And we're looking for T3. So we'll say T3 is mg, 3mg minus mg, which is 2mg. And then we have to find the tension in the right string. So let's do a force diagram of the block on the right. So that would have tension of the string on the block, and then it would have force of the earth on the block. And you know it's accelerating upward. This one's accelerating upward. So you would do, like the thing accelerates the system. So you have to decide whether this way is positive or this way is positive. So you can't choose up positive for both because they're connected as a system. So I'm choosing the way that they're moving as the positive direction. So for the block on the right, that means up is positive. So that would be G over 3 is equal to T1 minus mg over m. And then we're solving for T1. So T1 would equal 1/3 mg plus, minus mg? No, plus mg. So T1 is 4/3 mg. Okay, so we got those two. And now we want to get the rotational inertia of the pulley. So for that, we're going to have to analyze, we're going to do Newton's second law for rotation. So it'd be alpha, sum of the torques over I. So remember, alpha is A over R, right? And then the sum of the torques on this thing, the positive torques would be the counterclockwise torque. So that's T3 R minus the clockwise torque, T1R, all over the rotational inertia of this thing. Oh, they gave it to us. Whew, I didn't really want to derive that. Okay, so we're looking, I can't remember. We're looking for I. Okay, we got it. So solve for I, and you get T3 minus T1. You know what I could do? I could plug in T3 and T1. That might be nice. T3 is 2 mgr. T1 is 4/3 mgr all over A, which is G over 3. I got to multiply the whole thing by R. Okay, 2 minus 4/3, that's 6 minus 2/3. And the G, okay, well, 2/3 mgr squared over G over 3. And it's very nice. The 3's cancel, the G's cancel, and the rotational inertia is 2. Let's use the correct M. They gave us a capital M. Let's use the correct I. They said R, excuse me. R is R1. So I think we're good there, right? All right. We are going to continue the same problem. Try this one. Okay, I forgot the timer, so I'm estimating that was a minute. I don't know how my sense of time is, but okay. Angular speed of the larger pulley. Here's what we know. There's like a band. What do you call that? A belt. There's like a belt that goes around this system. So that belt, in order to not snap or to get slack in it, it has to be moving. Every part of the belt has to be moving with the same tangential speed. So we know that V1 is equal to V2, which means omega 1 R1 is equal to omega 2 R2. So we're looking for angular speed of omega 2 would be omega 1 R1 over R2, but R2 is 2 R1. So omega 2 is just omega 1 over 2. I hope I gave you don't have time to do that. The angular momentum of the larger pulley, that would be I2 omega 2. So that would be 16I1 times omega 1 over 2, which is 8I1 omega 1. Okay. And then we need the total kinetic energy of the system. So that would be 1/2 I1 omega 1 squared plus 1/2 I2 omega 2 squared. So now we're going to plug in our I2 and our omega 2. So it'd be 1/2 I1 omega 1 squared plus 1/2, what's I2? 16I1. Omega 2 is omega 1 over 2. So what does that do? So that's 8. 8 over 4 is 2. 2 plus a half. 5/2. I1 omega 1 squared. Yeah. Okay. I think we finally finished that problem. Oh, try this one. Okay, so I think you just draw a picture here. 2, 3, 4. So you have something that's starting over here. It's 2 kilograms, and it's moving from left to right at 0.8 meters per second. Angular momentum is mvr sine theta, but r sine theta is really the perpendicular component of r. So here's your origin, right here. So let's say we look at this position vector here. That's r, right? And theta is the angle between r and v. This is v. So theta is this angle. So r sine theta is really the perpendicular distance from the origin to the velocity vector. So we know what that is. It's 4. So we'll do mass 2 kilograms times velocity 0.8 meters per second times r, which is 4 meters. And if you plug that in, you should get 6.4 kilogram meter squared per second. So just because something isn't spinning, it still can have angular momentum. Okay, try this one. Okay, so you want to get the angular momentum of the rod about point P before collision. So the angular momentum of the rod would be I omega, and I of the rod, they gave it to us as 1/3 m1 d squared, and they gave us omega. So there you go. There's the angular momentum of the rod. B, derive an expression for the speed of the ball after the collision. Okay, so let's see. I was looking for some comment about, all right, we'll just assume angular momentum is conserved. So initial angular momentum is I omega of the rod, and final angular momentum is MVR of this point mass. So we already know I, 1/3 m1 d squared omega. Okay, that's the initial angular momentum of the rod. And then the final angular momentum should be m2 v times r. How far it is away? It's really r perpendicular, right? Let's put a little perpendicular sign there. The perpendicular distance is d. And we're looking for v, right? So we'll cancel one of these v's. So v would be m1 d omega over 3m2. Hopefully I did that right. M1, okay, great. And then assuming the collision is elastic. Elastic collision means kinetic energy is the same before and after the collision. So it'd be 1/2 I rod, right? Omega rod squared equals 1/2. The point mass is moving linearly, so it'd be m2v squared. So the rotational inertia of the rod is 1/3 m1d squared, and then its angular speed is omega. And we just found v, so why don't we plug that in? m1 d omega over 3 m2. I'm imagining we can cancel some stuff. So let's cancel one of these d's, one of these omegas. Oh, I forgot to square that. Oh, God, I forgot to square the v. Let's go back. I got to square all of these quantities here, don't I? Well, I'll just put a parentheses around it and square it. There we go. Okay, so forget about those blue cancel marks. I retract that statement. So it would be 1/6 m1 d squared omega squared is equal to 1/2 m2 m1 squared d squared omega squared over 9m2 squared. Okay, now let's do a little canceling. Okay, one of the m1s, the d squareds, the omega squareds, one of the m2s, and we're trying to get what? m1 over m2. So m1 over m2 would equal 1/6 times 9 times 2, right? 18, that's 3. Oh, that's a lot of work just to get 3, but I kind of like a clean answer. Okay, same problem. Okay, so what do we have here? Elastic collision. So we know that both angular momentum and kinetic energy are conserved. Let's start with angular momentum. So we got that. I erased it. Let me try to find it. 1/3 m1 d squared omega is equal to L final, which would be m1 v times the perpendicular distance, which is x. Okay. Now, we also know kinetic energy is the same before and after because it's an elastic collision. So we have 1/2 of I, 1/3 m1 d squared. Omega squared is equal to 1/2 m1 v squared. All right, so let's solve for v from the angular momentum, which would be, oh, couldn't I cancel that m1? That would be nice before I keep going. So it'd be, the velocity would be d squared omega over 3x. Hope I got that right before I go on. M1. Oh, gosh. Yeah, it has the same mass. That's fine. Well, I don't know. I didn't write it down. I'm just going to hope for the best. Okay. So on the right, over here on the kinetic energy, let's cancel the M1s and we can plug in our V. 1/6 d squared omega squared equals 1/2 d to the 4th omega squared over 9x squared. We got to get x by itself. So x is, I would really like to cancel these omega squareds first and change that. Okay, so it would be d squared times 6 over 18. Is that right? D squared over 3. Oh, that's x squared. So x is d over square root of 3. All right. All right. Rotation's not easy, is it? Try this one. Okay, so for this situation, what's important, it says rotating without friction. That means there are no external torques, so angular momentum should be conserved. Linear momentum isn't conserved because you have an external force, like there's an axle that is exerting a force on the rotating turntable, and it's not an elastic collision. Kinetic energy is not conserved. Okay, so I am going to leave you guys with this homework problem. When you do it, make sure you understand it's in the vertical plane, okay? And then next week, okay, so Monday, we're going to do kind of a dry run. It's going to be a 45-minute mock exam, and you're going to have 2 questions, just like on the exam. And it's just a chance. We're going to have a countdown timer, just to sort of get you prepared, get your desk all straightened out and make sure you've got your equation sheet. We're going to kind of go through the experience and try to treat it as seriously as you can so that you can kind of get into the routine. On Tuesday, we'll go over the solutions to Monday's mock exam. Wednesday, you're going to do another mock exam. So it's going to be 45 minutes, 2 questions. Thursday, you'll get the solutions to Wednesday's exam. And then Friday, we're going to do just last minute tips and tricks, logistical things to make sure you know how to log in, how to try it out beforehand, all that kind of stuff. Okay. So I look forward to seeing you on Monday when we're going to do an exam. So when you come Monday, be prepared. You're the one that's going to be working. Okay. You're the one. I'm just going to put up a question and then another question, and you guys are going to I hope you will be typing it like in Word or something, and to practice. Okay. So everybody, stay home, stay in your home, and study physics.